Bismillahirrahmanirrahim. Assalamu alaikum. So, today we will continue on the same chapter about the logical operations. If you remember last time, we have introduced the affine operations, if you remember right. We have said that the affine operations, they are called TRS, if you remember, which stands for translation, rotation, and scaling. Which will mean either zooming in or zooming out. If we want, for example, to enlarge or to shrink our image. And then after that, we have started introducing the logical operators, which can be summarized in general in this slide. Here we have mainly 4 types of logical operations. We have the AND and NAND. Okay? We have OR and NOR. We have XOR and XNOR, which is exclusive or exclusive NOR, and we have the NOT. Okay? Which is simply the negation of the values that we have. Of course, it's very easy to understand these operators if we are dealing with binary values. Okay? But when we talk about images, actually the values are to be represented, whether they are grayscale or color, they are represented in the form of integers. Right? It's not just a single bit. So how can we implement these operations on such type of images? Actually, we have mainly 2 ways of doing it. The first way is that we make some sort of analogy between the AND operation and some of the arithmetic operators that we have. So when we say we need to make an AND, okay, this will be represented or it will be implemented in the form of a multiplication. Okay? Here when we say that anything ANDed with 0 is equal to 0, right? Also here we say that anything multiplied with 0 will give me 0. Okay? Anything ANDed with 1, okay? Actually here it will give me the 1. Right? Here as well we can apply similar things. For the OR, for the AND we have said that we can use the multiplication. For the OR we can use the addition. Okay? We can use the addition. So here we say that if I want, for example, to make an ORing between 2 values, actually I can do it using the addition of these 2 values. But of course here, in order to have the correct effect of the ORing, we have to do some other side, let's say, operations or side process on these values. Okay? So this is one way of implementing such type of operations. The AND is represented by multiplication or is implemented by multiplication, and the OR is implemented by the addition. Okay? For the NOT, actually here if I have a certain value of x and I want to get its inverse or its NOT, or I want to apply the NOT operation in it, what I will have to do here is to subtract this x from its corresponding maximum value. Let's say I will subtract it from 255. So if this x, for example, is a grayscale level, if x here corresponds to a dark pixel, okay? If I make 255 minus x, this will convert it to a bright one. Okay? So if x is low, 255 minus x is high, and vice versa. Okay? This is one way of implementing this kind of operators, okay? By using the mathematical operators, the subtraction, the multiplication, and so on. There is another way of implementing the same thing, okay? Which by using what we call the same operators that we have. Here I will apply the AND operator, I will apply the OR, I will multiply the XOR. How this will happen? Here we have said that each pixel, if we take the grayscale case, is represented using how many bits? 8 bits, right? So if I have, for example, 2 images that I want to make ANDing between them, what will happen is that I will take the first 8 bits of the first pixel in the first image, and I will take the first 8 bits in the second image that corresponds to this pixel, and I will make a bitwise operation. Okay? So each corresponding 2 bits within these 8 bits, actually I will apply on them what? My logical operation. This logical operation can be an AND, can be an OR, XOR, whatever. Right? Understand the idea? So here what will happen is that, for example, if we consider 2 pixels and I will apply on them the bitwise operation, both of these 2 pixels actually are having different, let's say, grayscale levels. If I will apply the AND, I am sure that the resulting AND will have a value that is at least, it should be less than or equal to the smallest of them. Okay? Right? Because actually here if I have something like this, let's say 1, 1, 0, 1, 1, 0, 0, 1. Okay? And here I have 1, 0, 1, 0, 1, 0, 0, 1. Okay? If I will make the AND operation between them, what will be the result? AND operation. So I will have 1, 0, 0. Then I have a 1. Sorry, this one should be 1. Second. 1 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. And this is 1. If I look at this value, I will find that it is less than both. Right? If I will make an OR operation on the other hand, between them, what will be the result? It will be 1, 0, 0, 1, 1, 0, 1, 1. If I look at the result of the OR, I will find that it is higher than the highest value. Okay? It will be greater than this. So actually here, as you can see, we have implemented the AND, OR, XOR, and NOT, all of our logic operations using the logical operations themselves, but they are bitwise operations. Okay? The NOT here, it is simple, straightforward. Okay? Every 1 will be converted to 0 and every 0 will be converted to 1. Which is exactly similar to this equation, which is 255 minus x. Right? Clear? So, if you remember last time we have introduced a number of examples. Here we have said that, consider that I have 2 images. One of them is the image A, and the other one here is image B. These are my original images, okay? And I will make the different operations between them, okay? As you can see here, image B is a simple image. In this type of images in which we have black regions and white regions, these are binary images that can be used as mask to do certain operations. So here we can find something like this. If we assume that this is original image A on the left, original image B on the right, this is the result of negating each one of these images. So here on the left, here I have A prime, which is the negation that can be computed by 255 minus the value of the image, and this one is the negation of B. Right? So this one thing. Another thing here, if we look at the AND operation, okay? I want to make an AND between A and B. Okay? So anything that is equal to X, if we AND it with 0, it will give me 0. So here, as you can see here, in A ANDed with B, which is in the image on the left-hand side, we'll find that all of the values that correspond to the black part of image B will result in black part in the operation of A and B. Okay? And the part which is white in image B, it will be kept as is from image A. Right? Right. If I want to make an AND, this is 2 operations. First of all, I need to make an AND. Then after that, I need to invert this result. Okay? So here the black part has been converted into white part. And the colored part here, actually, I will have its corresponding photographic negative. Right? Which is resulting as well from 255 minus the image. Okay? So here we say that by ANDing the 2 images, dominant area of the masking image, which corresponds to B, it reveals a specific region of A. So here I am using image B in order to focus on a certain area in image B. Okay? So this is the example of the ANDing. If we look at the ORing here, we'll find that here on the left-hand side I have A or B. Anything ORed with the white pixel, it will give me white. Anything ORed with the black pixel, it will give me the same level of the pixel. So I will have something like this. Okay? So this means that I have removed part of the image. Okay? If I want to get the node again, I will take the OR and I will get its negation. Okay? 255 minus the value of this image. So actually this OR operation can be used in order to remove certain part of the image. Okay? Just to cut it away. As you can see from here. Right. Another example here, as you can see, is the exclusive OR. Okay? On the left-hand side image here, which is image number I, this is the result of A exclusive OR B. Okay? By definition, if we look at the exclusive OR operation, anything exclusive OR with 0, it will remain the same thing. Okay? So X exclusive OR 0 is equal to X. And this is what happens here. As you can see here, the normal image that appears near the boundaries here, actually this is the result of exclusive ORing with 0 of the image B. Okay? Anything exclusive OR with 1 will give me the inverse of this thing. So here, if I have X exclusive OR 1, this is equal to X prime. Okay? Or the inverse of X. That's what happened here in this small square, as you can see. Okay? So this will give me something like something that's called what? It's called binocular effect. Okay? This is the part that I want to focus on, and this part that I want to focus on, actually, I want to be represented with its photographic negative. Okay? The exclusive node, on the other hand, actually is the result of subtracting the exclusive OR operation, the result of the exclusive OR, from the 255. So I will have this image on the line. Okay? Right? Right. So this is for the logical operations. Let's go to the MATLAB. So now let's look at these examples that we have here. We'll start with example B in chapter 4, as you can see. Here we are just reading this image, which is called lake.jpg. Okay? Yes. Yes, I just want to go back through some small issues. Okay? Right. So here we will show it like this. Control C, Control V. And here, if you remember, this is the function which is called G_input. So actually, I will use the original image, okay, in order to create the other mask image, right? So here I will use the G_input, if you remember. And here we have said that we can select a group of points. Okay, and when we finish, we'll press and enter. So here the group of points actually are stored in M and N here, okay? So here we have the M for the number of rows. These are the corresponding values that corresponds to these rows, and N, right? Then after that, here we'll create the second image, okay, that corresponds to our mask, with the same size of X, initialized with zeros. And here actually the number of points that I have selected, okay, I will look for the smallest rectangle that can enclose all of these points, and I will assume that this rectangle will have the color Y. So here I will assign 1. Okay? So here it will be something like this: minimum N to maximum N, and minimum M to maximum M. For all of the 3 levels, okay, here we have this column. All of this actually should be initialized to 1. Here we have this one, something like this. Okay. I've normalized the values to 255. So now we have this second image, okay? Right? So the original image is the image of the lake, and the second image is this mask image. So now, see, we can get the inverse of this mask image. We can put it like this. And the inverse of the original image. And here we can show the inverse of the original image, which is this one, okay? It's the photographic negative of the original image. And also we can show the image of this is the inverse of the second image, right? Then after that, here, the operations that we are talking about. Here we have Actually, here we need to make an ANDing, but using the multiplication, right? So here we'll have something like this. Here in this statement, Control V. Actually, here what we are doing is that here we have one of the images, which is the X. It is of which type here? Unsigned integer. 8. And the G here, it is of type double. So here we should be very careful doing our multiplication. Here I will do the ANDing by multiplication. Okay? So here as you can see, here we have converted the X into double before multiplying it pixel by pixel with G. So the result here will be of which type? Should be of type double. Okay? So here as you can see, G1 is of type double. But here if I look at the maximum value of G1, it will be equal to 155. So the range is here, it is from 1, or let's say from 0 to 255. If I want to display it, in this case I need to normalize its value. Right? Okay? So, here, that's why here he is doing something like this figure. If I want to show this one, Control V, it will be something like this. So he has multiplied it with 0.00005. Now I want another way. Instead of multiplication, I want to divide it by a certain value. What is the value? What is the maximum value as a result of multiplication here? Yes? 255? Square, exactly. So actually here I should divide by 255 squared. Why? Because both of these two images at the beginning, actually before multiplication, the maximum value was 255. Okay? So here the maximum value of the result of the multiplication, it will be 255 squared. Simple. Okay? So here we can do something like this. Let's try it and see whether it will work or not. Yes, here we have it. Okay? Clear? Okay? So this is one thing. For example, now if I want to get, let's say, the inverse of this image. Okay? If I want to display the inverse of this image, what I should do here? The inverse of this image, which is the result of ANDing, this means that I want to the result of the NAND. Okay? What I should do here? Yes? Yes, here I should put 255 minus, or I should put off here?
We can assign all this to a new value.
Yes.
And then we can subtract it from 255, or we can make it to the power -1.
Yes, actually here I need to subtract this value from the maximum value that I can have. Okay? This value here is of which type? It is of type double. What is the maximum value of any pixel if I want to display it using the double? Is 1. Right? So here I can do something like this. Let's say I can make here 1.0 minus this value. What do you think? Clear? So this is the result of the negation of the original value, which was the result of the ANDing. Okay? Do you understand this case here? Here we have said that in order to make the negation or to apply the not operation, I need to get the maximum and subtract the image from this maximum value. If I would display the image as an unsigned integer, the maximum value is 255. If I will display it as a double, the maximum value will be equal to 1. So it will lead to the same result. Clear? Okay. طيب. Yes. Yes, احنا قلنا قبل كده we have said that here maximum something like this مثلا for example, okay? This type of matrices, as you can see here, if we take a look at the matrix X or G or whatever, this is a 3-dimensional matrix, okay? So I can get its maximum either by converting the matrix into a vector, and I will apply the max one time, or I can apply the maximum on this matrix directly, but for 3 times, okay? Because actually each time I will apply the maximum, it will reduce the resulting, let's say, matrix, it will reduce it by one dimension. So if I will make one maximum, it will reduce it to 2 dimensions. If I will make a second maximum, it will reduce it to 1 dimension, and so on. So here in this case, I need to get the maximum, okay, of any vector. First of all here, I need to look at its dimension. If its dimension is equal to n, this means that I need to apply the maximum n times. This is one way of doing things. Or convert the matrix into a vector and apply the maximum once. Clear? Type. Now let's look at something else now. If I want to apply the AND using the AND operator on this same 2 images, what I should do here? First of all, I need to convert both of the 2 images into unsigned integer 8. Okay? So here, if I look at the class of x, it is unsigned integer 8. This is correct. If I will look at the class of g, I will find that here it is equal to double. And the maximum value here in this g is equal to 155. Okay? Yes, because actually here we have normalized the image. G11 divided by 255 and so on. So actually here it was normalized.
So before the normalized, we can just subtract 255.
Yes. But after that, if I want to display it correctly, the result after the subtraction from 255, I need to divide it by 255 again. Okay? Yes?
Can you repeat the one that you just said?
The repeat?
Can you repeat what you just said?
We didn't say anything new. Okay, we have just said that. And put in mind, okay, if you are talking about a double valued image, okay, first of all, the maximum value in this case, it will be equal to 1. If it is unsigned integer, 8, the maximum value is 255. But if my image is the result of a multiplication of 2, let's say, images, the maximum of these 2 images is equal to 155. Right? And I found that, like in our case here, the result is of type double. Okay? So here, if I want to display it as type double, okay, I need to divide my image by the maximum value that it can reach. What is the maximum value of multiplying 255 by 255? It's 255 squared. That's why here we have divided by 255 squared. Right? We have divided by 255 here twice. Okay? Yes? Okay? Right? Right. Here, the idea, for example, if for this image, I want to display it, layer G1 here, I don't want to display it as a double, I want to display it as an unsigned integer. Okay? How can I do this? And here we have seen. Are you convinced that here, in order to display G1 as a double, I need to divide it by 255 squared? Do you agree with me? Okay? Here, this G1, as we have said before, this is the image, the result of the multiplication, right? So I need to display it. So before displaying it, I need to see what is its class. It is of class double. Right? So this means that the maximum, in this case, in order to appear correctly, the maximum should be equal to 1. Right? Type. As a result, G1 is generated from what? It's generated from the multiplication of 2 images. Both images, actually, they are having the maximum of 255. Okay? So the maximum of the result of the multiplication will be equal to 255 squared. In order to reach the maximum that is equal to 1, I need to normalize my image by dividing it by what? 255 squared. Okay? In order to display it as a double. Because 1 is the maximum of the double. Okay? But if I want to display this same image as an unsigned integer, 8, what should be the maximum here in this case? 255. Right? But the maximum of the result of the multiplication is still 255 squared. So to display this same image, G1, as an unsigned integer, using an unsigned integer type, what I should do here? I know that G1 alone, its maximum is 255 squared. I want to display it as an unsigned integer 8. So first of all, I will convert it into, actually I should not convert it now. First of all, I need to divide it by 255 because its maximum is 255 squared. So here in this case, I will divide it by 255. Then after that, the result, I need to typecast it like this. Okay? So here it was its double value has been divided by 255. Now I am sure that the maximum value is 255. But still this amount, it has the type double. So if I try to display it as is, I will reach the saturation. We'll find that maybe all of the pixels will have the white color. Okay? So first of all here I need to change its type to what? The unsigned integer 8. Let's see here what will be the result. Maybe it will not work, I don't know. No, it worked. Right? Yes, لأن احنا في المرة الأولى we needed to display as a double. So the maximum will be equal to 1. والمرة الثانية we needed to display as an unsigned integer 8. So the maximum is equal to 155. عشان كده المرة الأولى احتاجنا إن احنا نقسمها على 255 سكوير والمرة الثانية احتاجنا نقسمها على 255 only. Clear? طيب. Now I want you to look at something here. We have a relation or we have a function, let's say it's called bit and. Bit and. Okay? Here, let's assume that I have this value. Here I have A is equal to, let's say it is equal to 5. Unsigned integer 8, 5. Okay? And B is equal to unsigned integer 8. Let's say something like let's say 13. 13, yes. Let's put it like this. Or 9. Something like this. Okay? Right? We have a relationship here, or a function, let's say, function, which is called bit and. I can take two integer values, and I can apply on it the bitwise and. Here, if I have a value that's equal to 5 and a value that's equal to 9, what is the result of the ANDing between these two values? Who can tell me? If I will make it bitwise AND operation. What do you think? No, both of them they are of type unsigned integer 8. Right, let's see here. Here it is equal how much? Why it is 1? Yes. Yes. So let's see here the help of bit and. Okay. Why it's 1? خلينا ناخد another example here. If I have مثلا, let's say A is equal, instead of 5, it is equal to 8. And I have my B here is equal to 9. What will be the result of the ANDing between them? 8? How?
It's 0.
It's 8, yes, sure. It's 8. Okay? Because actually this is the only bit that will be remained. If I will make this kind of bit and operation, here I have, let's say, I have the value of 9, it was something like this, in 8 bits, right? And the value of 8 in 8 bits is something like this. And I will make a bitwise AND operation. So each 2 corresponding bits, I will make an AND between them. Okay? And the result, actually, I will compute it. So here 1 ANDed with 0 is how much? Is 0. 0, 0. This one is the only bit that will be equal to 1, 0, 0, 0. So here the result will be equal to 8. Right? Okay? We can apply this bit AND operation on the 2 images as well. Okay? But before applying it on the 2 images, I need to make sure that both of images are of type unsigned integer 8. Okay? We can see what will happen here in this case. Okay? But of course, in order to be on the same side, on the safe side, I need to ensure that each value that is added with other value, they should be of the same type and the same size. So before applying the bit AND operation, we have as well something which is called what, a bit OR operation. For applying this or that, I need to make sure that both of them are of type what? Unsigned integer 8. Okay? So here we have, again, here we have class of X is still what? Unsigned integer 8. Class of G is double. So this G actually I need to convert it into unsigned integer 8. Okay? Let's call it, for example, here we have X, let's call it Y. So here Y will be equal to unsigned integer 8 of G. Okay? It will not affect the appearance of the image itself. Okay? To make sure of this, I will display it. I will display this Y image. So we'll have something like this. Okay? This is the old mask that we are used to. Now let's apply the bit AND operation. And we can call it something like this. I will call it, let's say, AND image equals bit AND. And here I can give as arguments both of my 2 matrices. Here, of course, this operation to succeed, both of these 2 matrices should have the same dimension. Should have the same dimension. Okay? So here we'll do something like this here. We have let's see here whether we will have the correct image or not. And okay, so here we have the ANDed image. Okay, here we have the ANDed image. For the OR, do we have a bit OR? Yes, we have a bit OR as well. So here let's make something like this. Here I have OR image is equal to bit OR. Bit OR here as well is another function that can do the bitwise OR operation. Okay, so I will make the ORing of the X and Y bit by bit. So here we'll have this OR image and image. So here we have OR image. Sorry. Okay, so this is the result of the OR image. How can I do the negation? I can do 155 minus the value of the image. Now another question, how can I do the exclusive OR? Yes, there is a function. And if I don't have a function, how can I implement the exclusive OR? Using the AND, OR, and NOT. Here I have something like this. Here, let's say that I want to make X exclusive OR Y. This equal how much? X prime ANDed with Y, OR with X ANDed with Y prime. Okay? So here, we will write this equation here. Let's put it something like this. Here I have X OR image is equal to. Here, first of all, I will get the not X. How can I get the not X? 155 minus X. Okay? Right? This X prime, I want to AND it with Y. So here I will make something like this, and both of them I will apply on it the bit AND. صح كده؟ Right? And as well here I need to make the same thing. Control C, Control V. But here instead of 255 minus X, I want it to be with 255 minus Y. So like this I have made what? The X ended with Y prime. And these two expressions, I want to make an OR in between them. Okay? So here in this case, we'll do the following here. All of this actually should be enclosed here between big brackets like this. Put here a semicolon and apply what here? Bit OR. Now let's see here the shoe. It is called what? XOR image. Okay, so this is the result of XORing the two images together. Right? Again, if I want to get the negation, just subtract from 255. So this is straightforward. Okay? Type. Do you have any question about this part? Type. Let's go to the next part in our chapter here. Actually, here he talks about two things. We have something that's called noise. Okay? And something else that's called distortion. And we'll see here what is the difference between the noise and the distortion. So we'll start by the noise first of all. What do I mean by noise? Yes. Actually, for example, here while we are talking if we are talking about audio signals, okay? While I'm explaining here, and we have some, let's say, students that are talking outside, okay? The sound, in this case, can be considered as an additive noise to the class, okay? It may affect us. It depends on the level of the noise with respect to the level of my voice here inside the class. If the level of noise is considerable, in this case, actually, it will not be tolerable. Right? But if the level of noise is small with respect to the original signal, in this case, it can be tolerated. Okay? So in most of the cases, what we are trying to do, if I want to filter out the noise from the signal, I want to reduce the effect of noise. I cannot remove the noise 100%, but I can reduce its effect. Okay? Here, when we talk about images, we may have noise, and this noise actually it will be added during the operation of capturing the image itself. We have different types of noises, okay? So the coming slides, it will be nice for you to know, okay? I don't want the details of the noise. I want you just to know that we have this type of noise. So here we say that in a machine vision system, images acquired through modern sensors may be contaminated by a variety of noise sources. Yes. In most of the imaging applications where photo imaging is of concern, here we use cameras that are called charge-coupled devices. These charge-coupled devices, these are electronic devices. And when we talk about electronic devices, this means that we have electric signals, so this means that there can be some noise can be added due to different reasons. Here we say that we are used with photons that produce electrons. So here inside this charge-coupled devices, I have some sensors. When the photons are incident on these sensors, some electrons will be liberated, some electrons will be created or will be generated. And it will create a current. This current is proportional to the intensity of the incident light. Okay? And these are called photoelectrons. Okay? Here we have something that's called, accordingly, we have different sources of noise. We have something that's called photon noise, thermal noise, on-chip electronic noise, KTC noise, amplifier noise, etc. We have lots of noises. So we'll pass over them quickly. If we start by the photon noise, when we have an incident, let's say light, on this sensor, the number of liberated electrons actually it is not fixed. Okay? We have a certain probabilistic distribution of this photon. Okay? Maybe I may be targeting or I may be configuring my system telling that if I have this type of intensity, I will have this type of current or this value of current. But this is not always the case. This current will be generated with plus or minus error. Okay? I will not have this exact number of electrons will be created. So here I have certain probabilistic function of this form. I don't want you to go through the details of this function, okay? Just know that you have something like this. So nothing is deterministic here. It is probabilistic, okay? So here this probability, this means that this is the probability of having this, let's say, photon number generated, which is P, okay? Where rho here is the intensity, let's say, something that is called an intensity, it's parameter that's called intensity during a certain period of time T. It has this expression, okay? We'll not enter through this, let's say, information, the details of this information. Another type of noise is called the thermal noise. From its name, what do you expect to happen here? Here we have said that when I have set of photons are incident on these sensors, a number of electrons will be created and a current will pass. Okay? Some of these electrons are liberated and it will constitute the current, but they are not due to the incident photons. They will be due to the thermal, let's say, circumstances, due to the temperature that I have. When the temperature increases, maybe more electrons will be liberated, okay, independent of the incident light. So these excessive electrons that are created, we call it the dark current. Actually, this can be considered as a noise. Okay? It does not represent the image that I want to capture, actually. It comes from another source. Okay? So we will say that electrons are released due to thermal activity, indistinguishable from the true photoelectrons. Actually, these electrons with the photoelectrons will constitute the total current that I have. Okay? So here we say that dark currents can be measured for a particular environment. For example, at the beginning, I can detect what will be the average value of the dark current by putting the camera, for example, in a dark room and see what will be the output that comes from this camera. Okay? And afterwards, any image that will be captured, I will subtract this dark current from it. Okay? In order to reduce the effect of the noise. Okay? Do you understand the idea? So this is the main idea of the thermal image. Here we say that we have something that's called on-chip electronic noise, which is the chip that is responsible of capturing the, let's say, the image itself. It will generate a noise that is functioned in the frequency of the light that we have. As you know, this visible light actually it has different frequencies. Okay, starting from the frequency that corresponds to the red color, which is the lowest frequency, up to the maximum frequency of the visible region, which is the frequency of the violet color. Okay? Below the red we have the infrared, which we cannot see, and up and above the violet we have the ultraviolet, which we cannot see as well. Okay? So according to this frequency, I will have a certain noise will be generated. Okay? Another thing here that is related much more to the component that we use in order to build our camera. This camera is built of electronic components, as we have said before, transistors, like the field effect transistor. I think you have followed before a course about the electronics, right? Yeah. Did you study the field effect transistors? The FET? This is one type of transistors, okay? And this transistor, it will generate a noise voltage that has this expression, okay? It depends on three parameters, KTC. That's why here it's called the KTC noise, okay? Here the K is called the Boltzmann's constant. Do you remember this Boltzmann constant? Did you hear about it before in physics? No? So it's a constant value that is used in order to compute this voltage. And here we say that T here is the absolute temperature of the charged coupled device that we have. Okay? And C here is called the FET gate switch capacitance. So all of these things actually they are parameters that are related to the physical circuit that we use to build our camera. Okay? From it as well we can have this type of noises. Okay? Also we have the amplifier noise. This is well-known noise. If I have, for example, after capturing this signal it is of low level. I need to raise its level a little bit. So I will use an amplifier. These amplifiers, all of the amplifiers that we have, inevitably they will add additional noise. Okay? They will add additional noise. But how can I differentiate between one amplifier and the other? Is the ability of the amplifier to suppress this noise. Okay? What do I mean by suppressing the noise? Trying to minimize the effect of the noise. We don't have any amplifier that can prevent the noise 100%. Okay? Right. inside the MATLAB, maybe I will need to simulate this noise. Okay, so we have here a function in the image toolbox that is called IM noise or image noise. And here we can add different types of noise. We have something that's called what? Gaussian noise. Okay, this Gaussian noise actually has some sort of Gaussian distribution for its noise values. Okay, also here we have the local value. It's Gaussian, but it has a zero mean value. This means that the average here is equal to 0. The first one here, it will give me a white noise. Did you hear about this term before? White noise?
White?
Yes.
It's a good one.
No, it's not good. ما فيش noise that's good. يعني I don't have any noise, any type of noise. Actually, all noises are noisy. Okay? Here, the white noise, it means that it's, when we look at its frequency spectrum, I will find that it has components at different frequency values, but all of the components in the frequency spectrum are having the same amplitude. Okay? Right? Here we have another noise that has this kind of distribution that is related to Poisson. I think you have heard about this Poisson without going into the details of the Poisson. Here we have salt and pepper, where heat, for example, I will select certain points, certain specific points in order to add the noise. We'll see some examples of this. Okay? We'll see some examples of this. As well, we have something which is called multispectral noise. This is not an additive noise, but it's a multiplicative noise. It's a noise that will be multiplied by the value of the signal instead of adding it to the signal. Okay? So these are different types of noise. Also here we have some functions. Do you remember the rand function that we have seen in the C++ in Java? Here as well, we can generate random numbers in order to simulate noisy values that can be added to our signal. Okay? So this is for what? This is for the noise. What about the distortion?
Distortion is like effect in the original noise. It's not added.
It's actually, we can say that. Yes, can you give me an example? For example, in images.
But if I want to capture an image, I move my...
Yes. Which is called the blurring effect. I think what I mean by the blurring effect, or when the image is out of focus. Okay? Actually, this cannot be considered as a noise, but it's an error in the setting of the capturing device itself. I didn't, for example, adjust the focus in a good way. Or for example, while I took the image, as you have said, my hand was shaking. Okay? As a result of this, I will have this kind of distortion. Right? So, مثلا هنا we say that a more pertinent problem in photography scenario is that of distortions. Okay? Commonly called blurring. Blurring اللي لما تبقى الصورة مهزوزة. Okay? And it's treated as particular something which is called what? Point spread functions. Okay? Here as well, we have seen that if I want to implement or to simulate the effect of the noise on the images using MATLAB, we have the IM noise function. Okay? Here as well, we can implement the effect or simulate the effect of the distortion of the image. Okay? By taking something which is called what? Point spread function. Okay? So here we have, this is our point spread function. Here I am assuming that this is the result of taking the image of just one white dot here. Okay? When I take the image of just one white dot, I will find that the resulting image is something like this, as you can see here. This dot is blurred. Okay? So I will take this is called what? Point spread function. It's called point spread. This means that the point, its value, instead of being specific to its location, actually it has a spread effect on its neighboring pixels. Right? So this is called a point spread function. I will have a function that corresponds to this effect. Okay, I will call it a kernel, let's say. And I have my original image. This is the object that I want to capture. And I will apply this kernel on this object using the convolution. So the resulting image will be something like this. This is the original image, and this is the captured image with distortion. Okay? So this is the way how can we make or how can we simulate the distortion in MATLAB. Okay? First of all, here I need to create the kernel that corresponds to the type of distortion that I want to do. Okay? The type of blurring that I want to do. And I will convolve it with the original image. And this will be the result. Okay? So now let's look at mainly here for the distortion, the main problem that we have here is blurring. And for this blurring, we have different types. Okay? So we have something which is called linear motion blur. When I have, for example, something like this, I am holding the camera very good, in a good way, okay? And I want to capture this scene, okay? I will find that the things that are fixed will appear clearly, but things that are moving actually, it will be subject to the effect of the motion blur. Like here, for example, I have a bus that is moving in the background, okay? But the things that are fixed, like for example, this phone cabin, we have this, let's say, buildings, this man here, they appear clearly. So this effect is called what? A motion blur. Can I simulate or can I emulate this kind of effect or this kind of blurring in MATLAB? Yes, I can, as we'll see later. Actually, here the motion blur, for the time being, I will show you how can we apply it on the whole image, okay? But after that, we can select a certain region of interest in which we can apply this motion blur, okay? But I will show you how can we apply it on the whole image, okay? Now, let's look at something like this. Here we have another blurring, which is called out of focus blur. If I'm capturing, let's say, a scene in which I have objects at different distances. Some of the objects will be in focus, others will be out of focus. Okay? This is another type of blurring that can appear with the captured images. Also, we have something which is called atmospheric turbulence blur, due to the weather condition. For example, if I have rains, if I have dust, and so on, this will add some blurring effect on the image that I want to capture. Okay? And we have something else here which is called scatter blur. Scatter blur here, it is related to the refraction and diffraction of light. Okay? While I'm assuming that the light beam will go in one, let's say, in a certain straight line, due to some, let's say, we can say I have some non-uniformities in the surrounding or in the environment. These light beams, they may be diffracted, or it can be, for example, refracted. Okay, so this will result in some blurring. Like, for example, مثلا, in the very hot days here in Doha, okay, if you are stopping, let's say, in one of the traffic lights, and you go with your eyes through, let's say, the cars that are stopping, okay, all of these cars actually they are generating heat, okay. Due to this heat, actually, it will make some sort of expansion to the air. So you will say the scene is hazy, right? So this can be one of the effects that can go under this type of blurring, which is called the scatter blur. Okay. So here in this slide, we are just summarizing the noise and the distortion, the different types of noise and different types of distortion. So here we say that the noise can be treated as random numbers of certain distribution, either Gaussian or Poisson, okay, or salt and pepper, okay, which is called the spotted noise. And in this case, the noise in all of the times, in most of the times, are added to the image, okay. For the distortion, actually here, if I want to implement this distortion, the distortion is the result of convolving or making a convolution between the original image and the point spread function together. Okay? So one of them it can be implemented by addition, and the other one can be implemented by convolution. Okay? So what we will do next, actually, we'll see some examples of this noise and distortions in MATLAB. Let's go back to MATLAB here. We have. Let's clear. Do you have any question about what we have said so far? Any questions? So here we'll go to code C. Okay? In your book in chapter 4. Here we use this image which is called flowers. Control C. Control V. So this is the image that we will use in our example. Okay? For this image, actually, we will try to add different types of noise, and we'll see what is the effect of adding this kind of noises, and what type of functions we need to add the noise. So here we will need this size later. Let's just put it here. So here we have 1,440 rows and 2,160 columns. It is of 3 layers. It's a colored image. Okay? And here, this is the part which is important. Here, if I want to add or to simulate the effect of the noise on the image, I will take the array that corresponds to the image, or let's say the matrix that corresponds to the image here, which is X, and I will apply to it the type of noise using the IM noise function. And here the type of noise, actually, it will be enclosed between single quotes. Here it's Gaussian, with some additional parameters that are related to this type of noise. 0 and 0.1, this corresponds to the mean value, and this corresponds to the standard deviation of the Gaussian distribution. Okay? So actually here, this, when we apply this one here, we will see 2 different cases. One with a small standard deviation, and the other one with a bigger standard deviation, and we will see the difference. I will try to figure out why do we have such type of differences. So this is the first one. This is the second one. So, what is the difference between these 2 images here? Like this is the first one. راحت هنا الإيمج الثانية. Here we have the second one. Actually, both of these 2 images, they are having the same mean, which is 0. The mean value is equal to 0. So this means that only the image, the noise can have either positive or negative value. Okay? But here, as you can see, the difference is in the standard deviation. One of them, it has standard deviation 0.1, which is the image to the right, and the image to the left, it has a standard deviation of 1. Yet the standard deviation of 1, this gives me what? This gives me the information about that the amplitudes here are higher, right? Okay? This means that the deviation around the mean actually is big. Okay? But if the standard deviation is small, this means that the levels of the noise actually are lower. So that's why here we see that the image to the right actually is less noisy than the image to the left. Right? And in this case, actually, we can play with the parameter that corresponds to the standard deviation. Okay? Right. Now let's look at something else here. We have another type of noise which is nice as well, which is called salt and pepper. Salt and pepper, it is a type of spotted noise. Okay? And here it is written like this. Here I have same function IM noise. Here I have the image X. The type of the noise here, instead of Gaussian, here it will be salt and pepper with 0.05. 0.05, this will give me how much percentage of the pixels will be affected. So here when we say that 0.05, this means that this salt and pepper will appear in 5% of the pixels that we have. If I will put it 0.3, this will be in 30% of the pixels. So which one of them will be more noisy? The second one. Okay? So here, let's see here what will be the effect of adding this salt and pepper. It will appear in the form of spots, in fact. Okay? So this something like this, as you can see, it's specific spots. Okay? It doesn't have the continuous nature like the case of the Gaussian. Okay? So this is for the 0.05, for the 5%. If we apply it for the 30%, here it is. Sorry. So this is for the 30%. this one is for the 5%. Can you notice the difference between them? The quality? Yes.
They add black and white pixels. That does not mean that we are losing original data from the picture. For example, if we denoise it,
Yes.
the underneath pixels will be recovered, right?
Actually, here the denoising depends on your estimation, how you are going to denoise it. Okay? Because once you have, let's say, you have the original image value was X, and you have added to it delta X. So now, if you are going to apply this signal to your filter, now he sees the X plus delta X as a whole. But he cannot distinguish between which part will be the delta X and which part will be the X. It depends on your estimation and your prediction. And according to your prediction, you can design your filter. In most of the cases, as we'll see later, when we talk about the picture or these images in the frequency domain, this noise, they correspond to high frequency components. Okay? So we'll find that later, that most of the filters that are used in order to remove noise, they are low pass filter. This means that they will allow the low frequency to pass and they will suppress the high frequency. Okay? Which includes the noise. But as well, it can include part of the image as well. You see what I mean? But the noise, it has some low pass components, but that will remain with the original image. Okay? So here what we are trying to do, we are trying to minimize the effect of noise by applying this type of filters. But once the noise is added to the image, I cannot distinguish from now on whether this value, what part of this value correspond to the noise and what part correspond to the original image. Okay? I will try to do my best effort to remove as much noise as I can. Okay? You see? I don't have clear boundary between the original signal value and the noise that is added to this signal. Now let's look at the last part here, which is the distortion. And here we have said that the main type of distortion here is the blurring, right? So we'll use this signal, which is with this image, which is about the horses, if you remember this one. Okay. Right. And now, as we have said before, if I want to implement or to simulate the effect of the distortion, I will need to apply the convolution, right? So first of all, I need something that corresponds to the function that should be convolved with my image. So here, I will use the motion, let's say effect, the motion blur. So here I have some, let's say, function that will generate the filter that is needed for this. Okay? So here it's called F special. And here I have the type of the blurring, 15 and 45. 15, this means the distance that I will apply this blurring effect on. It will be applied to 15 pixels. And the 45, this is the orientation. It will be directed with 45 degrees in the positive direction, in the anti-clockwise direction. Okay? So it will go something like this, as if it is going in this direction. Okay? So here, first of all, we'll create the filter, and we'll see the filter, the plotting of this filter. It is something like this. Here, as you can see, it has minimum levels, it has 0 levels, then after that it will increase in this direction. This is the X and this is the Y, so it increases in the 45 degrees direction. Okay? Now this filter, we will apply it on the image using another function that is called what? IM filter, or image filter, that will take two arguments, the original image together with the kernel of the filter. Here, if we look at the size of the filter, here it is equal to how much? 11 by 11. Does it have any relationship with the size of the image in which it will be applied? No. No. Okay, that's why here it's called a kernel. So it will be applied on the pixels of the image, pixel by pixel. Right? So now let's look at the result of applying this blurring effect on the image. So here, as you can see, this image is blurred. Maybe here on the on the screen, it is not, the direction or the orientation is not that clear, okay? Because actually here we have lots of details. But you will find that, for example, if you take this waves, you'll find that it has certain peaks in this direction. Okay? So here, as if we have this whole scene was moving in this direction while I was capturing the image. You see? Now let's look at the focus blur. For the focus blur, we have another type of blur which has the form of a disk. Yes. Instead of motion, we have a disk, and 5 here, it will give me the diameter of this disk. Okay, diameter of this, actually it is 5 pixels. So now, let's make something like this, Control V. This is the result that we have. Here, if we look at F2 as well, actually, here 5 is not the diameter, it is the radius, sorry. Here it is the radius. So this is the F2 that is generated from here. So the effect of the blurring will be maximum at the center, and it will decrease as we go away from the center. Okay? Now, if you apply this filter on the image, this is similar to the out of focus blurring. See what I mean? It will be something like this. Okay? It has no direction of motion. Okay? What happens is that it is just the camera is not configured in the correct way. Okay? The focus is not adjusted in the correct way. Clear? Later, inshallah, in your project, we will need this type of functions in order to add certain effects, and we will apply on it certain filters in order to reduce this effect as much as possible. Okay? So maybe this type of, let's say, functions that we are using here, like for example the F special, the IM filter, the IM noise that we have seen in the previous examples, we may use them in our project. Okay? In order to simulate certain situations. Okay? Distorted images or noisy images. Okay? Do you have any questions yet?